In this video, we have another polynomial function, and we need to find all of the factors. We need to find all the zeros and all the intercepts. Unfortunately, we haven't been given anything. Like we weren't told what a zero was or what a factor was to get things rolling. So this is of degree 3. Now we know that as soon as we can get something to be degree 2, we're in good shape. So to go from degree 3 to degree 2, we just need to find one solution. And the way that we find that is by using the Rational Zeros Theorem. So in case you forgot what that is, that's where we do P over Q, where P is going to be a factor from the constant term, which is 6. So factors of 6 are 1, 2, 3, and 6. And Q would be a factor that's coming from your lead coefficient. So that again is 6, so you have the exact same factors. And what we're going to do is we're going to list every single possible combination between one of the numbers in the top and one of the numbers in the bottom. And that's going to give us our list of possible rational zeros, which means if there is a zero for this polynomial function that can be written as a fraction, it's got to be listed somewhere in here. Okay. Now again, this doesn't tell us anything about zeros that are imaginary or that contain radicals. So first, let's look at the number 1. 1 over 1 is the ratio of just 1. 1 over 2, 1 over 3, and then 1 over 6. Now we do the same thing with 2. Okay, so let's do 2 over 1. Okay, so that's a new one. 2. 2 over 2 is 1. We don't need to write that again. 2 over 3 is a new possibility. So 2 over 3. 2 over 6 reduces to 1/3, which we already have. All right, now we move on to 3. So 3 over 1. 3 over 2 is the combination we didn't have. 3 over 3 is 1, so we have that. 3 over 6 reduces to 1/2, so we already have that. Finally, 6. 6 divided by 1 is 6. 6 over 2 is 3. 6 over 3 is 2. 6 over 6 is 1. Okay, so if there's going to be a zero that's rational, it's got to be one of these guys, positive or negative. We just don't know for sure which one yet. All right, so I guess that means we need to grab a piece of scratch paper and do some synthetic division until we find somebody that works for us. Okay. Now remember, the quick trick to see if 1 works is to take these coefficients and add them together. If you take 6 plus 17 minus 5 minus 6, and it equals 0, if that happens, that means that x equals 1 is a 0. But we can see very quickly that that's not going to happen. That gives me 23 minus 11. That's not 0. So let's try negative 1. Okay, and again, this is my scratch work, so it's bound to be a bit messy as we just kind of go through this. So bring down the 6, multiply to get negative 6, that's 11, multiplies negative 11. All right, so we have a remainder of 10. Well, that did not work out right. What number should we try next? Well, I really don't want to try these fractions. I'm going to skip to the whole numbers because I feel better about myself when I do that. Right? So let's try using 2. So 6, 17, negative 5, and negative 6. Now if you look at this, here's 6, multiply to get 12, that's 29, times 2 is 58. This does not look like it's going anywhere good for us, right? We end up with 100 for my remainder, not 0. So we need to try something else, okay? And I think part of the problem here is that these two numbers were they were positive and they were kind of big. So when I started multiplying times 2, it's just making these guys bigger, and these negative numbers at the end were not likewise as big to kind of bring that down to something that was going to work out nicely for us. But let's try negative 2. Maybe things will work out better for us this way. All right, so bring down the 6, multiply, that's negative 12, that's 5, negative 10. You know what? I thought this was going to be it. No dice. Does not work out. Well, the next thing I would try is 3, but you know what? If I try 3, positive 3, I'm going to run into a very similar issue here. Because I would do 3 times 6 to get 18. 18 and 17 is 35. Multiply times 3 is going to get too big. So instead of doing that, maybe I try negative 3. Maybe negative 3 is going to work out for us. 6, 17, negative 5, negative 6. All right. So bring down the 6. That's negative 18. That's negative 1. Times negative 1 is 3. Gives me negative 2. Times negative 3 is positive 6. We get 0. That's the combination, right? It took us a while to get there, but we got there, and we didn't have to deal with fractions. Now, you could have tried 1/2 or 1/3, but I think it's in your best interest to stick to the integer values first. All right. So, coming back here to our problem, we said that negative 3 worked. All right, so we have the 6, 17, negative 5, and negative 6. I'm just going to write this here so it's nice and neat for us all. So that's 6 times negative 3. We said was negative 18. Combines give me negative 1. Multiply is 3. Add to get negative 2. Multiply times negative 3 to get positive 6. And there is your remainder of 0. All right. So here's something I want you to see going back to what Part A says. Part A says to write the function as a product of linear factors. Okay. So right now, here's what we have. My original function, 6x to the third plus 17x squared minus 5x minus 6 has already been factored somewhat. So since negative 3 gave me a remainder of 0, that means x plus 3 is a factor of this big polynomial function. And how many times does x plus 3 go into it? That's why we have the quotient. We now convert this. And this is 6x squared minus 1x minus 2. So this is that first stage in factoring the polynomial function. The first part is to find one of the zeros, which was negative 3, which would have come from the factor x plus 3. So we have a remainder of 0 from that division, and we take the rest of this stuff right here, and we write the quadratic from that, 6x squared minus x minus 2. And now we need to factor this, or try to anyway, right? Since the instructions say to write as a product of linear factors, it's kind of understood that this polynomial should be able to factor all the way. A quick check of this, 6 times 2 is 12. Are there factors of 12 that subtract to 1? Well, we know the answer is yes. We can use 4 and 3. So if you want to off to the side take care of that, the factorization, please do so. Now, I've been factoring for quite a while, and here's something that I already know. I know that 2 has to factor as 1 and 2. And if we were already working with the numbers 4 and 3, I've got to think about how I can get 4 and 3 from doing the inside and outside of this factorization, right? Well, the 2 is kind of a standout to me. 2 is not going to contribute to the 3. He's going to contribute to the term that gives you a 4x in the middle. So 2 is going to have to multiply times 2 over here, and 1 has to multiply times 3 here. And so you'll see that's 3x on the inside, 4x on the outside when you multiply these, and when you do the correct signs, that being a plus 1 and a minus 2, everything's going to work out. Now again, you can always take this off to the side, split up the middle term, do factoring by grouping, whatever it takes, and you'll still get the same answer. So this is the answer to part A. Now part B. Part B says to find all of the zeros. Well, since we have the complete factorization, this is like using the zero factor theorem. You're going to take each of these factors and write the corresponding zero. So this gives me the 0 of negative 3. And that makes sense because it's right here. It's the first guy we found. if I take 2x plus 1 and I set that equal to 0, you would subtract 1, divide by 2. If I set this factor equal to 0, I would add 2 and divide by 3. All three zeros are rational, which means they should all be found among the list of possible rational zeros according to the Rational Zeros Theorem. So let's slide this back up and let's take a look. So there's the 3. Of course, plus or minus, we don't really know what sign it's going to be, but we know it's negative 3 now. Was 1/2 available? Right here. And what about 2/3? 2/3 is right here. So all three rational zeros were listed. So we should know we're on the right track here. All right, so that's part B. Part C says to list all of the intercepts. Well, for the x-intercepts, all of these guys are real, so each one will correspond to its own x-intercept. So negative 3, 0, negative 1/2, 0, 2/3, 0. But don't forget, when it says all intercepts, that includes the y-intercept as well. So the y-intercept is going to be 0, comma, well, what was that constant term at the end? Negative 6. So 0, comma, negative 6. So there you have it. All of the zeros, all of the intercepts, and the complete factorization right here of our polynomial function. It says write it as a product of linear factors. Each of these guys is x to the first, so it means that's a linear factor. And from these linear factors, we were able to come up with the zeros, and each of those guys were real, and each one corresponded to an x-intercept. And remember, every polynomial function will have a y-intercept because the domain for every polynomial function is going to be all real numbers, which must include 0.